South Summit is really transformational. So many brilliant people from the world of business in Spain and all over the planet are gathered here over these 3 days. It's a way to do a year's worth of business in the space of a few days because all the right people are here. So it's all about networking, all about building your personal network. Please use all the tools that the organizers have very kindly put together to make the most of the event. So we're going to move on to our next brilliant keynote from one of the biggest technology companies on the planet. It gives me great pleasure to introduce to the stage to talk about creating meaningful brands and embracing technology. Please welcome Enrique Delgado from IBM. Enrique, thank you.
Thank you very much, Oysin. Okay, I'm going to talk about quantum computing applied to artificial intelligence. And I have to warn you a little bit at the beginning. There is going to be an initial part which is going to be a little bit theoretical, but I have to make it theoretical, otherwise you won't understand the rest. But at the end, it's going to be very practical. So those who are very pragmatic people, please bear on with me for a while. Let me start with a scene from a movie that I'm pretty sure, well, there's a lot of young people here, but I'm assuming all of you have seen this.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
Where the hell did you get that idea, Hal?
Dave, although you took very thorough precautions in the pod against my hearing you, I could see your lips move. So
this year is the 50th anniversary of this movie, which obviously is 2001 and Odyssey in Space. And it's obvious that in the last 20 years, artificial intelligence has advanced a lot. We have systems that can recognize images to a pretty good accuracy. We have systems that can play Jeopardy, chess, Go. We have, if you were attending Matthias' speech 2 days ago, we have even some initial robots that are helping people in the International Space Station to work. But the reality is that we are pretty far away from this type of intelligent system today. And I'm not even talking about the fact that there is this philosophical question about HAL having consciousness of himself. I'm just talking about the way that HAL talks with David, the fact that he can read the lips, the fact that he can understand human intentions. All these are things that one would expect from an intelligent entity, and we're still a little bit far away from that. What are the things that we have to do to reach that level of, let's say, HAL-like systems? I would say there are two main problems we have to solve. The first one is that at the end, any artificial intelligence feature is basically a big mathematical function that gets some data as inputs and gets some outputs. Depending on the type of feature that you are trying to create, whether it's recognizing something or understanding voice or predicting something, this mathematical function is going to be bigger, smaller, we'll have this shape or another shape. And one of the main problems of data scientists today is to find what's the best function that mimics an artificial intelligence feature. And there is actually today no way to know which is the best function to, for example, to recognize a picture. We know that convolutional networks work very well, but are the best possible function? We don't know. Data scientists work by trial and error. Okay? So this is a big problem, understanding what's the shape, what's the model of the functions that mimic intelligence. But let's assume that data scientists are very smart people, and they are for sure, and they solve this problem. And they know for each of the functions, for example, reading lips, what's exactly the shape of the function that they need. There is another problem. The other problem is that these functions are getting bigger and bigger and bigger. I mean, some of them have thousands, if not millions, of parameters and the coefficients that you have to calculate when you train them, and you have to compute. And this requires a lot of compute power. And today, since the beginning of computer science, to double the power capacity of a microchip, you have to double the number of transistors. And we are reaching the limit, basically. There is not much more way to go. At some point, the power of our computers will reach the point where these type of functions are not going to be feasible to calculate. And this is not a problem just of artificial intelligence. So relating the behavior of computing a function with the size of the input is a problem that has been studied in computer science for decades. We would say, typically, this is simplification, but bear with, to make my point, it's enough. There are like 3 types of problems or functions that change differently according to the size of the input. We have the problems that scale, we would say, linearly. For example, adding 2 numbers. If you add 2 numbers and these 2 numbers grow in size, the time, the effort that it takes to calculate the addition grows proportionally. Okay, fine. We have other problems, like, for example, testing if a number is a prime, that as the number grows, the effort that it takes to make that calculation grows polynomically. Could be to n to the squared, to the third, to the fourth, whatever. Okay? And then we have the really very, very nasty problems, which, as the size of the input grows, they grow exponentially. And the most famous problem is the traveler salesman problem. So the problem of a salesman who has to travel several cities and has to find the shortest path to cover all them. Okay? For these problems, at some point, there will be no computer capacity that is able to solve the required function to solve the problem. To have, let's say, a more graphical picture, imagine that this line goes out of the screen and then out there and go out to the city, and we reach a point where it's at the level of a building. And imagine that the level of the building is the time that it takes to calculate the effort to calculate, for example, adding 2 numbers for a certain input. When we reach the level of a building, for a polynomial function, we would be out of the atmosphere. And the graph of the exponential function would be out of the known universe. So this is the proportion of the magnitude of how difficult are these problems here. So what can we do? There is only one thing we can do, is change the way we make calculations. There is nothing more we can do. And the answer is quantum computing. So quantum computers, I'm not going to explain how they work, but basically they exploit quantum effects in subatomic particles to make calculations, to store and operate information, and have the property that can reduce a lot the time it takes for some of these problems to be calculated. A lot, I mean a lot. For example, the most famous problem ever on quantum algorithms is the problem of factoring. So factoring a number in 2 primes, it's a very well-known problem because all the cryptography that you use in your phones, in your computers, is based on that. It's the RSA protocol is based on that. In a classical computer, what it would take 28 trillion years, I don't know how to say that number, in a quantum computer could take 100 seconds. This is the level of speed up, of efficiency that you can get from a quantum computer. Does that mean that every problem that we have in a classical computer, we put it in a quantum computer and suddenly it speeds up a lot? Not at all. Absolutely not. It depends on the algorithm. You need to find the right algorithm so that it can speed up. Okay? For example, the traveler salesman problem, which was possibly the nastiest problem that goes in this line, most possibly we will never find a quantum algorithm that speeds it up more than a quadratic factor, meaning that in a classical computer it could take 100 days, and in a quantum computer it could take 10 days. Okay? So it depends very much on the algorithm. Actually, the real magic of so building a quantum computer is really tricky, but the real magic is in the algorithm. How does this apply then? Let's go back to artificial intelligence. To artificial intelligence. Well, in artificial intelligence, there are like 2 or 3 problems that would fall in the category of the really nasty problems. But most of the rest of problems fall in the middle one, because basically artificial intelligence is about doing linear algebra operations. And linear algebra operations are operations that fall in the polynomial scaling, no more. The problem with artificial intelligence is that the size of the inputs is so big that even if the scaling is not the worst possible one, you still have a tremendous effort to calculate big functions. Okay? The question is then, okay, do we have quantum algorithms to help us speed up the way we train functions? And the answer is absolutely yes. Actually, all the ones you have here have a quantum equivalent to speed them up. The most famous one is this one, the matrix inversion problem. That's a problem that in a classical computer, it has a scaling of n to the third, but in a quantum computer, it has an exponential speed up, so the same type of speed up that we saw in the factoring problem. The problem with this algorithm and with many of the artificial intelligence algorithms is that most of them expect the input data to come in a quantum format. And moving classical data into a quantum format, it's not difficult, but it has a cost. And if you have to do it many times, and in artificial intelligence you have a lot of data to move to quantum format, then the cost of moving data from classical to quantum may compensate the speed-ups that you have with these algorithms. Okay? But there are exceptions. And the most prominent exception is the support vector machine. Those who work in artificial intelligence, I'm sure you know what it is. For those who don't, support vector machines is an algorithm that classifies data in two categories. For example, patients who may develop cancer versus patients who may not develop cancer, or mail that may be spam versus mail that it's not spam. It just classifies into two sections. And the way to do it is you represent the data in one space, and you find a line where all the category of one of the categories goes into one side of the line, and in the other side you have all the other categories. The problem comes when you have data like this. Imagine that this is data, and you have to find a line that separates on one side all the dark colors, and in the other side all the blue colors. If we have data like this, you cannot do it. It's impossible. You cannot find a way to make this separation. But there is a trick that you can do, and it's to move all the data into a higher dimension. In this case, if we move all the points to a second dimension, then finding a line, this line here, that separates the data, it's very easy. And this is exactly what support vector machines do. They take the data, they move it into a, let's say, higher dimensional space, and they find the line where the data is separated into. And in quantum, we can do it much faster than in classical computers. And the good news is that if today you go home and there is nothing in TV, or there is something in TV and it's very boring, you can connect to the internet and try the quantum algorithm for that in a real quantum computer. Because in IBM, we offer to any of you 4 quantum computer machines for free, which are these 4 here. You see that they are from 5 qubits to 16 qubits. Qubits is the basic element to store quantum information and manipulate it. Okay? And you have to think that every time that you add 1 qubit to a machine, you are doubling the power of that machine. So if you move from 16 qubits to 20 qubits, you are not just increasing the power a little bit. You're increasing the power 16 times. So it's a very big increase. Okay? The question is here, possibly, okay, and with 20 or 50 qubits machines, the 50-qubit machine, we have the prototype. It's been fine-tuned now, and should be available soon. I'm not exactly when, but it's already there. But the question again is, with a 15-qubit machine, can we do something that with a classical computer we would never do, even a supercomputer? And the answer is no. The expectation in the community is that the first applications that will have a business result that you will never achieve in a classical computer will arrive when we get to the 100 qubits. Now, you have to take into account that we went from 5 to 20 qubits in 2 years. So reaching the 100 qubits, it's really a very near future. It's not something for 10 years. I'm not sure if it's going to happen next year or the other one, but it's really, really close. And meanwhile, you can prepare yourself to take advantage of this and do something that you will never be able to do in any cloud or any supercomputer in the world. The next question is, okay, I want to try it, but I have no idea how to program a computer or how quantum computer works. No problem. There is an open source called Quizquit. I'm not sure if I pronounce it correctly, but I call it Quizquit. Which basically, it's a set of Python libraries. So Python is a language that almost everybody knows, especially if you work in artificial intelligence, that provide you with all the elements that you need to program very easily a quantum computer and connect to the computers that we have in IBM in our data centers. You have demos, you have tutorials, and everything is in GitHub. So if you want to go to GitHub and download the software, it's, well, tonight you can do it if you want. Even more. There is a module in Quizquit called Aqua, and Aqua has specific libraries to solve specific type of problems. So we have a module with libraries for chemistry, and you may wonder, why chemistry? Chemistry because it is believed that the first applications that will have one of these, let's say, benefits that you will never get in a classical computer will come from modeling molecules. So the pharma industry, for example, is really very, very much after the chemistry results of quantum computing. You have a module for optimization problems. For example, the traveler salesman problem is an optimization problem, or things that have to do with Monte Carlo methods. And of course, you have the artificial intelligence modules, which basically code the algorithm of support vector machines that I just explained. So it's really, really very easy to start and start playing around with it and learning so that when the first really big machines appear, you can take immediately a benefit of that. It's true that some of the companies that we have been collaborating to develop quantum are very large companies. But the reality is that this is most of the people who enter into the free quantum computers, or even in the most powerful ones, are startups. Because this is the perfect field for a startup to start developing things that no one has developed before. And if you enter into this link here, you will find the list of the top startups that are collaborating with us. For example, Zapata is a very well-known one, which is collecting all the algorithms in quantum that are appearing, because every day appear new algorithms, and you can check what they are doing, and you can even have reach agreements with IBM so that you can use not only the free computers of 5 and 16 qubits, but you can use also the 20-qubit machine or the 50-qubit machine when it becomes available. Okay? Just to finish, I have put you here what I think are the key links that, if you're interested in starting to play around with this, you need to consider. The first one is the quizquit.org website, where they will explain what is Quizquit, what is being developed, etc., etc., etc. Here you have the link in GitHub to Quizquit, so that if you want to download it and start developing things in Python, you can do it now. And if you want to contribute, you can do it, of course. Here you have the link to the portal where you can access the IBM devices, the quantum IBM devices. It's very easy. You only have to register with your mail and password as anything, and you can start playing around with that. And if you are really interested in understanding the science and the deep technology behind all these systems, just enter into our research site, and there is a section on quantum computing with all the, let's say, more scientific papers, which are very interesting. If you're interested in these things, I always say that it's the perfect storm between physics, mathematics, computer science, and engineering. And it's really very, very beautiful. So if you like the science, here you'll find many, many things that I believe are very interesting. So that's it. I hope you like it. Thank you very much.